Hello engineers, today we will be covering short circuit calculations for low voltage systems. Let's see some important formulas first. Source impedance is equal to base MVA by source fault level. Actual resistance equals Rs into L divided by N into 1000. Where R is actual resistance, Rs is resistance of cable per kilometer, L is length of cable in meter and N is number of runs. The same formula applies to reactance, you just need to replace Rs with XS. The values for Rs and XS can be found in the cable data sheets. Per unit impedance equals actual impedance by base impedance. Same formula applies to per unit resistance and per unit reactance. Next is base impedance, which equals base kV square by base MVA. We need to calculate the per unit values relative to the new base values by using both the old and new values. Also check out formula for the impedance. Our final outputs are as follows: the fault MVA, which is calculated as the base MVA divided by the total per unit impedance, and the short circuit current, which is obtained by dividing the fault MVA by the product of √3 and the base kV. We will now work through this example. The source fault MVA level is specified as 500 MVA. The length of the cables, number of runs, size, as well as the cable's resistance and reactance are provided. The resistance and reactance values can be obtained from the cable data sheet. Let's quickly review the flow of the example. First, we will determine the source impedance, followed by the per unit impedance ZA between the HT panel and the transformer. The total impedance Z1 at the transformer will be the sum of the source impedance and the impedance ZA between the HT panel and the transformer. After calculating the impedance at the transformer, we can derive the fault MVA and short circuit current at the transformer. Next, we'll calculate the transformer impedance using new base values. Then, we will find the impedance ZB between the transformer and the main LT panel, with details provided. The resistance and reactance can also be obtained from the sandwich bus duct data sheet. Following this, we will calculate the total impedance Z2 at the main LT panel by adding Z1, the transformer impedance, and ZB. With these values, we can determine the fault MVA and short circuit current at the main LT panel. Subsequently, we will calculate the impedance ZC between the main LT panel and sub-panel 1. The total impedance Z3 at sub-panel 1 will be the sum of Z2 and ZC. Using these values, we can find the fault MVA and short circuit current at sub-panel 1. The same steps will be followed for sub-panel 2. First, we need to establish the base MVA and base kV. We will set the base MVA at 2, according to the transformer rating, with the base kV for the HT side as 33 kV and for the LT side as 0.415 kV. The source impedance, according to the formula, is the base MVA of 2 divided by the source fault level of 500, which results in a value of 0.004. Let's proceed to the next step. We'll calculate the actual resistance using the formula shown on the screen. The resistance value is taken from the datasheet. The length of calb is 40 meters with single run. After inputting the values, we get an actual resistance of 0.0064. Now, let's calculate the base impedance using the values provided on the screen. The base kV on the HT side is 33 kV, and the base MVA is 2. This gives us an impedance of 544.5 ohms. Next, to find the per unit resistance, we'll divide the actual resistance calculated on slide 8 by the base impedance. The result is 0.0000118. To calculate the actual reactance, follow the same steps as for resistance, but substitute the reactance value from the datasheet. Input the new reactance value, keeping the length and number of runs the same. This will give the actual reactance. To calculate the per unit reactance, simply divide the actual reactance by the base impedance. This will give you the per unit reactance value. Now, we can calculate the per unit impedance of the cable by combining the previously calculated values of per unit reactance and per unit resistance. Impedance of cable will be 0.0040146. Therefore, the total impedance at the transformer Z1 will be the sum of the source impedance and the impedance of the HT cable. The fault MVA at the transformer can be calculated by dividing the base MVA2 by the total impedance up to the transformer, resulting in a fault MVA of 498.18. Next, to find the short circuit current at the transformer, use the formula as fault MVA divided by √3 into base kV. Our short circuit current at transformer will be 8.71 kA. Now, let's calculate the impedance of the transformer at the new base. The old impedance is given as 0.06. Since the transformer kV and MVA values are the same as the base values, the impedance will remain unchanged. However, you can use the same formula shown on the screen if you choose a different base MVA. Let's move forward to determine the impedance between the transformer and the main LT panel. We can calculate the actual resistance of duct using the formula, which yields a value of 0.000414. Since we are now on the LT side, the base kV will change, which will also affect the base impedance. The new base impedance can be calculated using the formula, base kV squared divided by base MVA. By substituting the values of actual resistance and base impedance, we can find the per unit resistance. Similarly, we can calculate the actual reactance using the relevant formula, just as we did for resistance. Then determine per unit reactance. By using the per unit reactance and resistance, we can calculate the impedance of the duct. Therefore, total impedance at the main LT panel Z2 will then be the sum of Z1, transformer impedance and impedance of the duct between the transformer and the LT panel. With the impedance calculated at the LT panel, we can now determine the fault MVA and the short circuit current as shown. To calculate the impedance between the LT panel and sub-panel 1, we first need to find the actual resistance of the cable. Since the total number of runs is 14, you can use the formula for resistance, which typically incorporates the length of the cable, the resistance per unit length, and the number of runs. Then calculate per unit resistance. Similarly, calculate actual reactance of cable. Then calculate per unit reactance. Using the actual resistance and reactance values, we can calculate the impedance of the cable. The total impedance at sub-panel 1Z3 can be expressed as 2 plus cable impedance. Determine fault MVA and short circuit current at sub-panel 1. To determine the impedance between sub-panel 1 and sub-panel 2, we will start by calculating the actual resistance of the cable. Since the number of runs is 5, you can use the formula for resistance, similar to the previous calculation. Then calculate per unit resistance. Similarly, calculate actual reactance of cable. Then calculate per unit reactance. After calculating the actual resistance and reactance, you can determine the impedance of the cable between sub-panel 1 and sub-panel 2. The total impedance Z4 at sub-panel 2 can be calculated as addition of Z3 and subsequent impedance of cable. Calculate fault MVA and short circuit current at sub-panel 2. Finally, we have determined the fault MVA and short circuit current at transformer, main LT panel, sub-panel 1 and sub-panel 2. This comprehensive analysis allows us to understand the fault conditions at each level in the electrical system, helping to ensure proper protection and performance.